Benford's law gives us the expected patterns of the digits in tabulated accounting and finance data. And in this case, we will be looking at some technical issues related to how to measure conformity to Benford's law, as well as how we could actually use Benford's law to detect fraud, at least the fraud that occurred in the Health South case of many years ago. We're going to be using the census data. We'll use census data because it's easy to understand. The data set is not too big, and it's worked very well for a couple of years now. So we are going to take our data from this file, and what I'm going to do is the links to all the files will be at the bottom in the description. We're going to take our data, we're going to copy it to the Negrini cycle template, and we are going to run the test and look at our first and second digit graph. My data, all the way down to row 3143. So we can simply do copy, go to the data tab here, paste. Basically the data that was there was simply there so that if you clicked on any of the graphs, you got something as opposed to a blank graph. And if you clicked on the tables, you didn't get divisions by 0 and the like. So that was just a placeholder. To run the tests, I need to go here. I need to copy these formulas down to the last row, and the way I can do that is by going with a plus sign. There the plus sign appears. There it's not. There it is. And a swift left double click copies the formulas all the way down to the bottom. And number 1 says my first digit graph. There it is. Take a screenshot of just the graph, and that would be your answer to number 1. And for number 2, a screenshot of your first 2-digit graph. That's how easy it is. It took Benford 6 years to do 20,229 records. He did it by hand. It took us less than a minute to do 3,143 records electronically using Excel. What level of conformity does the data have to Benford's law? And what we are going to look at now is the first 2-digit mean absolute deviation. And the mean absolute deviation, here you can see we have the Benford line, and actually over there we have a minute deviation. But what we look at is we look at each of these deviations, which is the difference between the actual and the expected. Here we go. The actual is slightly below the expected. So these are the digit combinations going from 10 to 99. These are the expected Benford's law proportions. And under Benford's law, I expect 4.1% of my numbers to start with 10, and just under 0.5% of the numbers to start with 99. And we get this pattern going down. These are my deviations. I'm under, I'm over, I'm on the line. We take all the deviations, and it doesn't matter whether the deviation is over or under. We take the absolute value, and then we take the average of these absolute values, and we get something called the mean absolute deviation. The bigger these deviations are, the bigger will be your mean absolute deviation, and that is calculated for us right over here. Tables, right down at the bottom. My mean absolute deviation 0.00143, and that is the answer to number 3. Oops. Calculated. What level of conformity does it have? Just remember that number 00143 when we go to the book. We're not using the first digits, we're not using the second digits, we are now concerned with the first 2 digits, and I had 00143, which fits in right there, and that is acceptable conformity. You might find that the results from a first digit test and the results from a first 2-digit test or a first 3-digit test are slightly different. So at least I need to go right here, first 2 digits, acceptable conformity. Divide your data into 2 random samples And now we're going to run the Negrini cycle test on both samples. What I'm going to go here, this is my first run. I'm going to go and I'm going to save this file, save as, and I'm going to save it as part 1. The reason is Excel does not like we have files open with the same name. So we'll do open again, and I'm going to open the Negrini cycle again. Let's go and do what it says. Divide the data into 2 random samples of 1572 and 1571 records respectively. So we'll go here, and what I'm going to do is I'm going to do a random number here. And we can do that using equals rand. There. This is a random number between 0 and 1. I'm going to copy it down, get the plus sign. It's copied all the way down. Now I have a random number next to each, and I'm going to sort this, but when I sort it, it'll recalculate the random number. And what it says is do 4 descending sorts. So sort, descending is largest to smallest, 1. And it's actually randomized this over here. Sort, largest to smallest, 2. It rearranged all this, and it recalculated. Sort, largest to smallest, 3. Sort, largest to smallest, 4. Now I'm actually going to get rid of this so that we don't it doesn't do a recalculation again. And my first random sample would be my first 1572. So we need to go down here. I could have used F5. 1572, which would be on row 1573 because there's a header row. So this would be it. This would be the new sample. So, and what I'm just going to do is color that yellow, knowing that the second sample starts there. This is the first sample, 1572 rows. Up. I could have used F5. And now we go copy, but is the Negrini cycle open? Yeah. I opened a new fresh copy. Here it is. Did I get the heading? I think I got the heading. Paste. So now I have half my numbers. Copy down. And now it's run the first digit test. There's my first digit graph. There's my first 2-digit graph. Bit more messy, as you might notice. And what does it say? Stager 2 used the first 2-digit MAD. So I've done the first 2-digit test. You can see this graph doesn't look as great. Tables down below here, and I'm just going to make a note of this. I get 0.00206, which is higher than what I had before. And now we'll run the second one. And actually, I might as well just stay here, go to data. Since I've run this, I'm going to delete this here. It's easier than opening up a whole new Negrini cycle. Clear contents. And then we go and get my second sample. There it is. And the second sample started here. And we just have to remember that I don't have the heading. Doesn't matter about that little yellow highlight. Copy. And start here. Paste. Copy down. First 2 digits again, it changed. Mean absolute deviation, 00187. Therefore, what we had is 00187 for this sample, 00206 for the first sample, and they were 50% samples. And then for the population, 00143. Let's go back and look at the requirements. Show a screenshot of your first 2-digit graphs, which meant I should have done a screenshot after I did that first one. What level of conformity do the two random samples have to Benford's law? First 2-digit mean absolute deviation. State the two values and classify as either conformity, acceptable conformity, and the like. This was sample 1. This was sample 2. Oops. And this was the population. And we really don't want to format that with zeros. We'll just do that. There we go. So the population at 00143 was acceptable conformity, and both of these are greater than 0018. Both of them are greater than 0018, and they actually fall into this category here, which is marginally acceptable conformity. So what happened was I divided my data into two 50% samples. The mean absolute deviation, the fit to Benford's law, deteriorated. This is a worse fit. The deviations are larger, and it went from acceptable conformity to marginally acceptable conformity on both counts over there. We ended up with marginally acceptable conformity. And this is basically state for the population, state for the, did the population conform best to Benford's law, and indeed the population at 00143 was a better fit to Benford's law because the mean, the average absolute deviation is smaller. You can look at the three graphs and you should see that this one beats the other two hands down. We will add 1,000 fictitious counties to our data, and then we are going to run the test. But first, why are we doing this? These are some PowerPoint slides from my class from a few days ago, my Accounting 501 class. We were talking about fraud, and I said, I'm concerned that what a controller might do is simply do a journal entry like this: debit accounts receivable, credit revenue. $20 million, $20 million added to revenue. The $20 million will flow through because it's fictitious, and our net income will be overstated by $20 million. What you might tell me then is a controller won't do an entry for $20 million. The auditors will find it. Let's have a look at the Health South fraud. Weston Smith, I know Weston, I like him. He's an excellent public speaker. Weston Smith published this article in Issues in Accounting Education, and it was basically how I started to do my fraud and what I did. This is Weston and I. This is 2016, Minneapolis. We were both giving presentations at the workshop for the chapter, and this is a photo of Weston in action. But we get back to Weston's article. It says, auditors are taught to look for trends or unusual changes. We knew that. So we ran analytical reviews, also called analytical procedures, on ourselves to determine where we could safely book our bogus earnings. We didn't want any of our ratios to be out of line and have the auditors look a little deeper. The journal entries were kept below 5,000 to avoid detection by the auditors. They knew that the auditors only looked at journal entries that were $5,000 and higher. In other words, the auditors would have looked at a large journal entry like that. So what they did was they broke them up into little chunks. The entries were kept below 5,000 to avoid detection by the auditors. They knew that because they would hire the auditors to come work for them after the auditors had been on the Health South audit, and that's how they found out what the auditors' thresholds were. At the end of this repeated exercise, over 126,000 fraudulent journal entries were posted quarterly. 126,000 fraudulent journal entries were posted quarterly. If we multiply this number by 4, because there are 4 quarters in the year, that would mean it's a little over 500,000 fraudulent journal entries, all below 5,000. And this fraud worked. It worked for years. It was big, and it worked brilliantly. If you want to read it, you can. This was an email from Weston just a few months ago, and we know each other, and we enjoy exchanging emails from time to time. So let's get back. So what I did was I sort of invented some county data. Here it is. And I invented population numbers that were below 5,000, but higher than 2,000, because why do a fraudulent journal entry for 50 or 100? It's not going to help you very much. So I kept my numbers from 2,000 to just under 5,000. And I have 1,000 of them here. So you can see state, FIPS, non-existent county. I made up an area, can't remember where I got that from. And here we go. These are all fake numbers. And I'm going to do exactly what Weston did. These are my numbers. I'm going to do copy, and I'm going to go back to that part 1. Here it is. And I'm going to go to the bottom. Got to get to the bottom of this. There it is. And now I'm going to do paste. So here I have my good, real, authentic data. Here I have my fraudulent county numbers, and it's all the yellow going down to the bottom. So now what I do is I do this, and I need to get this analyzed, so I need to copy these formulas down to the bottom, and we get the plus sign and a swift left double click. There we go. And now let's see what we're asked. We will add 1,000 counties to our data, use the data set, copy the numbers to where I did, run the Negrini cycle tests, so a screenshot of your first 2-digit graph. The nice thing is, oops, I needed that part 1. The nice thing is the first 2-digit graph is here, and let's see whether it deteriorated or not. So let me just check that I'm in the right data set, and indeed I am. First 2, there it is. And you can see what's happened. All my numbers were from 2,000 to just under 5,000, which means they all had first 2 digits from 20 up to 49. And when I added all these numbers in that range, 2,000 to 4999, first 2 digits 20 to first 2 digits 49, I now get this little mountain in the middle here, and this would be a major clue that my data has numbers that are set in a specific range, and I have too many of them in that range. You can see the 20 to the 49 all higher than expected, and all the others have deteriorated to being lower than expected. Well, not exactly there, and not exactly there and there, but almost. Good enough for me. Show a screenshot of your first 2-digit graph, and we just did that. What level of conformity does the fraud data have to Benford's law? Remember, the good data was 00143. What do you think this graph is? I have lots of deviations here. I have lots of deviations here, much larger than before. It should be higher than what it was. Here we go. 00341. And if I go to my chart, it's above that. It is a serious case of non-conformity. In fact, it's at least 1% higher than above 0022. What level of conformity? Non-conformity. Did the level of conformity improve or deteriorated? The level of conformity most definitely deteriorated. And that is case 4.1. This will be your final screenshot. I hope you've enjoyed it. We looked at Benford's law. We looked at the mean absolute deviation. We saw that when we took the data and broke it into two 50% random samples, the mean absolute deviation deteriorated, which should tell you that if I have small data sets, I'm going to get a larger mean absolute deviation just because smaller data sets have larger mean absolute deviations. And if I inject fraud numbers, as they did in the Health South fraud, I think Benford's law could have found it. Thank you. Bye-bye.